Assalamu alaikum students. Article for today is Ampere's law. Ampere's law, which is also known as Ampere's Circuital law, has a very great importance in electromagnetism. Initially, Biot-Savart law basically explained that B can be determined through any current element. And after Biot-Savart law, Ampere, Andre Marie Ampere in 1826, he was the person who explained that we can determine a magnetic induction or B at any point in the integrated magnetic field in particular loop, and he related that integrated magnetic field in a loop around the current carrying wire is basically related to the, or you can say directly proportional to the current which is passing through that wire. So in this particular law, what we determine, we basically determine B in this particular Ampere's law, right, where at any point in that particular magnetic field, right, we can determine B in that particular geometry, which is known as Amperean loop. We will discuss what is Amperean loop later on. So basically, Ampere's law explains to how you can determine a magnetic field at any point near to or any point on far from that particular conductor and so on. We already know that current is basically responsible for producing the magnetic field, right? So we usually say that I is directly proportional to B, right? We know that when the charges start moving, there is a magnetic field around them. So if there is a current carrying wire, then definitely there would be a magnetic field, as you have read in the previous articles. So consider there is a straight current carrying wire, and the current which is flowing through it is in the upward direction. Now if you notice that if this is current carrying wire and I amount of current is flowing through this particular wire, what would happen? Magnetic field will establish, and if I draw that particular magnetic field using right hand grip rule, what would be it? If I grasp this particular conductor in my right hand, and the curl of the finger would indicate the direction of magnetic field, if only if the thumb is indicating the direction of the current. So this would be the direction of B, which is definitely in the anti-clockwise direction. As we know that in this particular case, there would definitely be lots of circular paths around this particular wire. Obviously not a single one, like if I can draw, there would be a lot of magnetic field, magnetic loops, which are indicating the magnetic field. And we know that as we move away from this conductor, definitely the magnetic field would be weakened, and if we are getting closer to that particular conductor, magnetic field would get stronger. After knowing all this factor, what is the next thing? Next thing is basically the permeability factor. Now what is basically the permeability? Whenever field, this magnetic field is within the conductor, that is okay, but when it comes out of that particular conductor, what could happen? Like in this particular figure, what is going to happen? This magnetic field is now basically interacting with the medium. That medium could be free space, or that could be air, or so on, whatever medium you are choosing. So this particular medium is basically responsible to change that magnetic field, right? Obviously this is the property of the medium, that how it is allowing the particular magnetic field to interact in that particular medium. So we say that medium basically absorbs some of the magnetic field, and what we acknowledge or what we observe is basically the leftover, right? A little amount of is that particular magnetic field is absorbed by that medium, and the leftover is definitely, which is obviously the greater amount, is absorbed by us. And this is basically observed by a factor which is known as mu naught. This mu naught is basically the permeability of free space, and if there is another medium other than free space or vacuum, then it would be represented by simply mu. Now, considering the fact that what should be our requirements to determine B in this particular case, so I believe that if I'm having infinite number of loops around this particular current carrying wire, then how can I determine magnetic field at any particular point? So for that purpose, what we have done, consider there is the same case. We are having a current carrying wire, and definitely field, there is a lot of field lines. I am going to draw an Amperian loop, because I have been asked to determine at this particular point P, that you have to determine B at this particular point P, right? I have to determine B at this point. So for that purpose, what will I do? There is a huge number of field lines around this particular current carrying wire. So what would I do? I will draw an Amperian loop. Now you must be thinking, what is an Amperian loop? Amperian loop is basically an imaginary surface, just like you have drawn Gaussian surface, right? So Gaussian surface, and what you have done in Gaussian surface is basically some kind of a surface which is drawn near to or exactly on that particular point, which is close to the conductor. So in case of Ampere's law, this Amperian loop has been drawn. Obviously, it can be in any shape depending upon our feasibility. So in this case, we have drawn it in the circular path, right? Because why we have done this? Because it is providing us the symmetry, right? Amperian's loop basically require is having some kind of characteristic. What sort of characteristic? Number one, Amperian loop can be in any shape drawn according to our feasibility, but Amperian loop should be drawn in such a way that at any point on which I want to determine the magnetic field, that point should be on or near to that particular Amperian loop, right? So in this case, we observe that P is basically on the Amperian loop, number one. Number two, that for Amperian loop, B should be uniform. Like at every point on this Amperian loop, B should be uniform, right? How can we say that? As you can see, there is a distance r, which is basically the radius, is definitely same throughout this particular, it would be the same value, it is having the same value throughout the loop, right? And at any point, if I want to observe the direction of magnetic field, I am observing that this direction is basically the circular one. And if I want to determine B at this particular point, I will draw a tangent on this particular point. If I want to determine B at this point, I will draw a tangent at this point. And if I want to determine B at this point, I will draw the tangent at that point, right? So we observe that B is basically circular, and at any point if I want to determine, I will draw the tangent and determine the direction of B. So we observe that for every point there is R, and R is basically equal, as I've told you earlier, that R is basically equal to every side. When R is equal from every side, that means the magnitude of B is constant. When magnitude of B is constant, obviously B changes if R changes, right? So if like if I say in this particular diagram, if I see that R is if having the value of this, and if in this case R is having the value of this. Why we are saying that? Because we know that as you move away from the conductor, B reduces, That means if you're increasing the r, the value of r, b is getting reduced. So in this case, r is constant, that means b is constant, right? So if r is constant and b is constant, that means magnitude is constant. What about direction? Direction is tangential at every point. So ultimately we say that b is constant in this particular case. Now the second condition of our Amperean loop has been satisfied in this particular Amperean loop, which is circular. Third point. Third point for Ampere's law, Amperean loop, is basically that b and L, that is the length element. And what is the length element? Like first let me explain that. This whole Amperean loop is basically divided into small number of patches, or you can say current element or the length element, right? And one particular length element or the current element is basically represented as delta L or simply dl, right? So this current length element is basically obviously it is having the same value throughout the loop. And if I want to determine this particular value at any specific particular point, like if I want to determine at p, I observe that the value of length element is like this. Like if I want to draw it like that, I would definitely show it in this case, like it would be like this. So this is the direction of dl, and at this particular point, if I want to draw the direction of a magnetic field, it would be tangent at this point. So this is the direction of b, and this is the direction of, in the black I have shown the direction of dl. Now what you observe? You observe that b is parallel to dl or delta L, right? At any point, if you observe, like at this particular point, I will see that the direction of b is tangential. And if I want to determine show the direction of L at this particular point, which is along a line, it would definitely be like this. And then the path will definitely be curved. So at every point, b is directly proportional to b is parallel to L, that is the length element, and we say that theta in this particular case is equal to 0. There is a symmetry, which is basically b is parallel to dl. So this is the third condition, which says that b should be in magnitude and in direction as well, should be uniform, right? So I have described the three conditions for Amperean loop. Now moving towards the next step, b basically is having a strength, and we have seen that thing, and the direction we have already seen that what angle I'm getting. Now choosing the current element we have chosen at every point, and the current element is basically that particular length from which current is passing, right? So it is also known as current element or the length element, whatever you want to say. Now we have already discussed that in this particular figure, what we observe, that I have the same condition of current flowing through this particular wire, and there is a magnetic field around this particular wire. Now I have been given the fact to determine b at this particular point p, and definitely radius would be equal to r. Direction of b, if I want to determine the direction of b at this particular point, it is tangent to that particular loop. And if I want to determine the direction of length element at this particular point, suppose this is a length element, then it is having a direction that is equal to dl, right? So we see that b and the length element, they are having a parallel case, and theta would be definitely equal to 0. What we observe that for this particular length element, if we take the product, that is b into dl, it is having some kind of value. If there is another path for that length element, there would be definitely again a b, which is definitely uniform. Like suppose the value of b is 10, right? And their length element is of 1 meter. Consider that there are 100 elements that we have drawn, right? So if I say that for this particular case, for this particular length element, what would happen? b into dl, b value 10, and dl having a value of 1. So for this case, the product of b and dl would become 10. For this case, 10. For this case, 10. For this case, 10. For this case, suppose we have divided into 100 length elements, then what would happen? 100 into 10, right? So it would become that the value would become overall b dot dl for this whole of the loop, it would become 1000, right? For one element, b dot dl, and then comprising all of those current elements, when we calculate the value of b dot dl for whole of the loop, it would become 1000, right? So that means if I'm choosing, suppose in a condition that I want to really choose another loop, right? There is another loop I have drawn, and consider that for this particular loop, what is going to happen? We know that the value of r would definitely be greater. When the value of r would definitely be greater, that means b is getting smaller, right? According to the condition that b is inversely proportional to r, which we have already studied in electrostatics and electromagnetism as well. This is the property of the magnetic field lines. So b is inversely proportional to r, that means b would decrease, right? When b would decrease, so what we do to make that product of b and dl constant, so what we are going to do, we will definitely increase the length element, right? Now the length element would be greater as compared to we have taken previously. Now you see that this is dl, this is dl, and you can see the value, the length or element in this case is greater, and we are increasing the value of dl, the product of b dot dl. If I'm increasing the factor of dl, what would happen? B would decrease. B is already in the decreasing mode, so b is weak in this region, so it is having a less value, and so we have increased the dl. And ultimately what we observe that in this case, suppose the value of b is 5, right? And then now the length element in this particular case, suppose it is 10, right? So in this condition, what would happen? Like condition would be in this particular. Okay, so suppose again, if the length element has been increased, suppose the value of it is taken as 5, and overall the divisions would be equal to again 100. So overall length would become like 555 for 100 length elements, it would become 500. And now the magnetic field has been decreased. Earlier if I had taken its value to be 10, so suppose now its value is 2. So 500, like the product of b dot dl, 500 into 2, it would again become 1000. So what we basically observe that for every case, like if I'm taking dl equals to 1, or in the other case if I'm taking dl equals to 5, then overall length in this particular case for 100 length elements, it would become 100, and for again 100 length elements, it would become 500. for this particular case, because this is near to that particular conductor, so the value of B in this case is greater, which is equal to suppose 10, and for the greater radius, the value of B is considering it to be 2, then the product of B dot dl in this particular case, it would definitely would be like 10 into 1, which is basically equal to 10, and B dot dl in this particular case, it would become 5 into 2, which is again 10. Or if you are taking it in terms of length element, overall length for the whole loop, then what would happen? I would definitely will multiply B dot L. Now if I multiply B into L, it would become 1000, and in the other case, if I multiply B with the L for the whole loop, this 500 multiplied by 2 would be equal to 1000. So ultimately we observe that the product of B dot dl or simply B dot L, it is equal to constant, and this particular constant is basically equal to the current. So I would write this B dot dl phenomena, it is equal to the current and mu naught times of current, where what is mu naught? Again, this is the permeability. So this is basically the statement, or you can say the formula for Ampere's law, and how can we state it. So for getting the statement of Ampere's law, we state it like the integrated magnetic field in a particular loop, the product between both of them is basically equal to the current passing through in that particular loop into mu naught. What, and mu naught, that is the permeability of free space. So that's how we can define the Ampere's law, or we can state the Ampere's law. Ampere's law is also known as Ampere's Circuital law. This Ampere's Circuital law, what does that mean? Why this name is given to it? Because for every configuration which you will notice, we will observe that we have drawn Amperean loop just like Gaussian surface. We are going to draw a closed figure, right? In this case, you can observe there is a closed figure which is circular, and in the next cases you will again see that we are going to draw the Amperean loops of obviously of different geometry, but definitely they would be again closed loops. So this Ampere's law is basically for the closed surfaces. That's why it is known as Ampere's Circuital law. That is basically, circuit is basically anything which is closed, any surface which is closed. So this is also known as Ampere's Circuital law. Okay. Now, if I want to determine the relation for Ampere's law for the statement, we have observed that B dot dl is equal to mu naught I. This B dot dl, or you can write it as like delta L, as written in your book, B dot delta L. This is equal to mu naught I, right? This B dot delta L, if I want to open this dot product, obviously this is the dot product between the two vectors, and if I want to open this dot product, I would write B delta L cos of theta, and this is equal to mu naught I, right? And this theta, we have already discussed that for any point in that particular loop, the value of B and delta L, the angle between both of them, would be equal to 0 degree. So I can write B delta L cos of 0 degree is equal to mu naught I, and cos 0 degree is equal to 1. So B delta L is equal to mu naught I, right? And because since you are not the student of mathematics or engineering, pre-engineering, so that's why I'm not going to discuss the integral form of this. this word, that is integrated magnetic field, which you have seen in your book. uh, if I want to write in that term, I would definitely represent this integral. This integral, this is the integral sign, right? For that means that the whole surface has been integrated or divided into number of parts, right? In number of patches or number of paths or number of current element or length elements. And this circular little circle on this integral, it is represented that for a closed surface. So, integrated closed surface, what is integrated? That is magnetic field is integrated, and the product with dl. And what is dl? Dl is the length element, and the product between both of them, it is equal to mu naught times the current which is flowing through that particular loop, right? Sorry, loop nahi, that particular conductor. So this is basically the relation through which we can also discuss. So don't get worried if you see Ampere's law with this particular formula. This is also correct, this is also correct. And last but not the least, I have discussed earlier that Ampere's law can be related to Gauss's law. Gauss's law was an application to determine E at any point in the electrostatic field, and Ampere's law is basically and a law which through which we can determine B at any particular point in that particular field. So that's all for today's article. This configuration which we have studied is basically applicable on a long, infinitely long current carrying conductor. And if the conductor is infinitely long, definitely we have to choose the finite portion of that infinite long current carrying conductor, and we will apply the same phenomena. So this was the article for today. And coming towards the applications, that along the straight line and along the um, solenoid, we will determine the magnetic field in the next articles. Thank you so much.